Hello, welcome to this lesson on electrical resistivity. This is part 1 of 2, and in part 1 we're going to cover the basics, and in part 2 we'll look at some calculations. We're going to find out what resistivity is and what this equation means. To help us do this, we need to consider the factors that affect the resistance of a length of wire. So we've got a diagram showing a wire of length L. Current's going to flow through the wire in one face, out the opposite face. And the cross-sectional area we're calling A. Don't mix this up with the surface area of the sides. The cross-sectional area is the area through which the current is going to flow. What factors affect the resistance? Well, there are key factors we're going to look at. The length of the wire will affect the resistance, the cross-sectional area will affect the resistance, and the material the wire is made from will affect the resistance. Let's start by looking at how length affects resistance. Let's compare a 1 meter length of wire to a 2 meter length of wire. The wires are otherwise identical, the same material and the same cross-sectional area. To compare them, we can imagine applying 12 volts to the ends of each wire. We'll get a current through the first one, a current through the second one. Which current do you think would be biggest if we applied 12 volts to each wire? The answer is I1 will be biggest. You can probably guess that. Let's put some numbers in to help see what's happening. Let's suppose I1 is 6 amps. We then find I2 is 3 amps. Let's look at the resistances of the wires. We're applying 12 volts to the top wire and the current is 6 amps. The resistance is voltage over current, 12 over 6, it's 2 ohms. The bottom wire has a small current, 3 amps. Let's work out its resistance. It's 12 volts over 3 amps, which is 4 ohms. Can you see what's happened? The wire has doubled in length and the resistance has doubled in value, 1 meter to 2 meters, 2 ohms to 4 ohms. It doesn't have to be doubling. If it had made the lower wire 17 meters long, we would find the resistance is 17 times bigger. It would have been 34 ohms. And we can summarize up that sort of relation by saying the resistance is proportional to the length. Other factors being kept constant. Resistance is proportional to the length. Let's try and explain why that's true. There's two ways you could look at it. If we join two 1 meter lengths of wire in series, it's like joining two 2 ohm resistors in series. That would give us a total of 4 ohms. So you could think of the fact that resistance is proportional to length as following on from the way we add resistors in series. A more fundamental way of thinking about it is to ask what the cause of resistance is, and it's energy loss due to collisions as the charge carriers move through the wire. If they've got to move twice as far, there'll be twice as many collisions. We're doubling the number of collisions. That's why the resistance doubles if we double the length. Now, let's look at the effect of cross-sectional area on resistance. Do something similar to what we did a moment ago. We'll have two wires. One has got a cross-sectional area of a square millimetre, 1 square millimetre, and the other 4 square millimetres. If you're good at maths, you'll probably know that the bottom wire has twice the diameter of the top wire. We'll do the same as we did. We'll apply 12 volts across each wire. What we might get is for the top wire 6 amps, but for the bottom wire 24 amps. What's happened is the current is 4 times bigger in the bottom wire. Let's work out the resistance. For the top one, voltage over current 12 over 6 is 2 ohms. For the bottom one, voltage over current is 12 volts over 24 amps. It's half an ohm. What's happened is making the area 4 times bigger has made the resistance 4 times smaller. Say that again. Area 4 times bigger, resistance 4 times smaller. And we can summarize that by saying resistance is inversely proportional to A, which we write as R is proportional to 1 over A. As the area gets bigger, the resistance gets smaller, and vice versa. And we can ask why. Why should that happen? And there are different ways you can think about that. You could consider what would happen if we took 4 of the smaller wires and put them in parallel, which is the top part of the diagram. That's equivalent to the bottom wire, because the cross-sectional area is 4 square millimeters. The shape is not critical, it doesn't affect things. And we know from the way that resistors in parallel combine that 4 2-ohm resistors in parallel gives a total of half an ohm. Try that if you don't believe me. So the 4 wires at the top, each with a cross-sectional area of 1 square millimeter, behave the same as the 4 square millimeter wire. So the resistance dropped because we combined resistors in parallel. That's one way to think about it. Another way to think about it, more fundamental, is that the total number of charge carriers is 4 times more in the bigger wire, assuming the wires have the same length. If you counted the number of conduction electrons in the top wire and the bottom wire, equal lengths of both, you'd find the bottom wire has 4 times as many conduction electrons. That means it's 4 times better at conducting, means its resistance is 4 times less than the top wire. Let's look at the effect of material on resistance. Let's recap. Resistance is proportional to length. Resistance is inversely proportional to cross-sectional area. We can combine these two to give us resistance is proportional to L divided by A. Now we can take this proportionality, and turn it into an equation. That would be R equals some constant times L over A. This constant depends on the material we've used, and it's got a name. It's called the resistivity of the material. We give it a special symbol, and the special symbol is this Greek letter. It looks like a P, but it's not. It's rounded if you look at the shape carefully. And this letter is a Greek letter rho, and it's a symbol for resistivity. So we've ended up with this equation that resistance is the resistivity, each material has its own value, times the length of wire divided by the cross-sectional area. What units does resistivity have? Well, we'll start with this equation. R is rho L over A. Rearrange it to make rho the subject. Resistivity is the subject. Rho equals RA over L. Let's put some units in. Resistance is ohms. Area is square meters. And divided by the length in meters, we end up with this expression, which simplifies to ohm meters. Notice that's not ohms per meter, it's ohms times meters. Ohm meters. That is a unit for resistivity. Here are some examples. Now, resistivity varies with temperature. Things increase or decrease their resistance as they get hotter or colder. So the resistivity of a material depends on its temperature. So strictly speaking, you should say what the temperature is when quoting a value of resistivity. For silver at 20 degrees C, it's this value, 1.59 times 10 to the minus 8 ohm meters. That's a very small value. Silver is a very good conductor, and metals have small values of resistivity because they're good conductors. An insulator like glass will have a high value. There are many sorts of glass, but as a ballpark figure, the resistivity of glass is about 10 to the 12 ohm meters, a big number. There are substances such as silicon which are kind of midway between metals, good conductors, and insulators. For example, silicon has a resistivity of 60 ohm meters, and you'll find different values if you try looking it up. It depends on the purity of the material. Notice the value is kind of middle midway between the conductors and the insulators. That's why silicon is referred to as a semiconductor. Its resistivity is halfway between a good conductor like a metal and a good insulator like glass. Not really halfway, but somewhere in that region. Let's see if we can come up with a definition of resistivity. Imagine you had a cube of material 1 meter by 1 meter by 1 meter. Now you wouldn't do this in practice, but it's just a conceptual thing. We know this formula, resistance is rho L over A. Let's put some numbers in for this cube of material. Let's imagine we're measuring the resistance between the top and bottom faces, opposite faces. The resistance would be the resistivity of the material times the length, well the length from top to bottom is 1 meter, divided by the cross-sectional area. Well, the cross-sectional area would be 1 times 1 square meter. That would leave us with R equals rho. That would be true for this cube, providing it's 1 meter by 1 meter by 1 meter. And we end up with this definition. The resistivity of material is a resistance between opposite faces of a 1 meter sided cube of the material. You may want to think about that. Make sure you understand it. Well, that's it. In part 2, we'll take a look at some calculations and their solutions using the equations we've looked at.